Okay, welcome along. Video about moments. Sort of trying a slightly different format where I've actually pre-found some definitions. They're not quite right, so I'll talk about them and then we'll get into kind of showing you how to do some moment stuff in action. Principle of moment states that when an object is in equilibrium, the sum of anti-clockwise moments about any point equals the sum of clockwise moments about the same point. I think you can write that faster. Principle of moment states that when an object is in equilibrium, the sum of clockwise moments is equal to the sum of anti-clockwise moments about any point. We use that quite a lot, so that'll be okay. It should make sense. The moment of force is the product of the force and the perpendicular distance between the axis of rotation and the line of action of the force. I think you can replace axis of rotation with point, and that will save you a little bit. A couple is a pair of forces equal in magnitude but opposite in directions whose lines of motion do not coincide, and I might draw a little picture of that. I can't write where I've cut and paste for some bizarre reason. The centre of gravity is the point in an object through which the entire weight of an object may be considered to act. I think it's better to say where the mass appears to be concentrated for slightly technical reasons. So I won't say anything more about the principle of moments, but the definition of the moment of a force is, here's our point, here's our force, and here's our distance measured perpendicular to then the moment of the force is just FD. Obviously has units of Newton meters. A couple is two forces acting in opposite directions that don't go through a single point. And obviously the thing is that this only has a rotating effect because there's no overall force in any one direction, and the moment of that force taken about any point is just FD. So obviously D is the perpendicular distance between the two forces. And then if you want to find the centre of mass of a shape, you might have done this. We get an irregular shape. If we hang it up so it pivots freely, we know for sure that the centre of mass must lie on that line. So if we then hang it up kind of differently, so there's that line. It's got on both occasions be hanging underneath the pivot point, so that is the centre of mass. So I think students do find this sort of moderately difficult to use to solve problems. We'll start off by just thinking about the seesaw type problem. Usually this is the one that students find easiest. So we might have a force of 8 newtons on this side, just kind of coming up with easy. A distance of 3 meters away from our point where we're going to take moments. The fact that it's the pivot isn't really crucial. It's just easiest in this case. So if this is 4 meters, what force acts here? So the principle of moment states that the clockwise moment, which in this case is 4 meters times a force we don't know, equals the anti-clockwise moment, which is the force, the distance of 3 meters times 8. 3 8s are 24. So question mark is 24 over 4. Question mark is 6 newtons. It isn't really mathematically much more complicated. Oh, just another thing. So that means, assuming the beam is light, that must be a force acting up here of 14 newtons to keep it in overall equilibrium, because forces up must equal forces down. So we often, well, people talk about a uniform beam. That means that the weight is distributed uniformly along it. So say this beam has mass, weight 20 newtons. And we might be told that the beam has an overall length of 4 meters. And there might be an object placed on the beam, and that might have a mass of 10 newtons. And we might be asked to find the two forces acting up, which are going to form our equilibrium. So we know to start with R1 plus R2 must equal 20 plus 10. I'm just going to rub this out. That's left over from the question before. And it's just kind of confusing the matter now, isn't it? Right, so R1 plus R2 must equal 20 plus 10 equals 30 newtons, and we'll use that later. But the main thing we want to do is take moments. So I've said with the one extra distance that we'll need is 1 metre. So we're going to take moments about here. We're going to take moments about the force R1. So the force R1 isn't going to appear in our working because it has no distance. So when we take the moment of R1, we get 0 times R1, which is 0. So it doesn't have any effect. So we're going to take our clockwise moments to start with. And there are, this is acting clockwise, about here. And this is acting clockwise. So each time we do force times distance. So we've got a force of 20 newtons and a distance. Well, what's the distance? Well, the beam overall is 4 metres long. So this distance here must be 2 metres because it's a uniform beam. So the weight must act in the centre. Plus the moment of this force here. And that's got a force of 10 newtons. And that's at a distance of 3 metres. And that distance there is 3 metres. And that seems to be the bit that gets people. We're always going for our moment being about exactly the same point. So that's 10 newtons. We don't actually need to write the unit in, do we? Times a distance of 3. And that then equals our unknown force of R2 times the total distance, which is 4 metres. So 2 20s is 40, plus 30 is 70, equals R2 times 4. So R2 is 70 over 4, which I'm pretty sure is 17.5 newtons. And then if you look back here, we know that R1 plus 17.5, just substituting into here, equals 30 newtons. So R1 is 12.5 newtons. And I think I'm going to stop there because I think last week's video was a bit too long. I hope you found that useful.